Well, good day, everybody. This is Chris back with the Ancient Scholar, and today I'll be talking about barbiturates and benzodiazepines primarily. Barbiturates and benzodiazepines are two very common, the benzodiazepines being more common in contemporary times, but are two very common, what we know as CNS depressants. They are commonly prescribed and commonly abused, and so there's certainly something to talk about that's noteworthy when it comes to looking at toxicology. Okay, so let's go ahead and start real quick talking about the nervous system, particularly what goes on at the molecular level of the nervous system. And it's interesting to know that when you talk about amino acids, of course, we have several, a couple dozen fundamental amino acids that are then stuck together and folded together to make the primary, secondary, tertiary, quaternary structures of proteins or proper proteins. But amino acids themselves can actually act as neurotransmitters, and one such case is the amino acid glutamate. So let's go ahead and just put that up there for you guys. Glutamate. Glutamate is an amino acid. It's very common. In fact, it is the major, what's known as a fast. Okay, it's a major fast neurotransmitter in the central nervous system. And it is the most common overall neurotransmitter. So it is the most common overall neurotransmitter in the central nervous system, and it is the major excitatory neurotransmitter that we have in our central nervous system, at least in mammals. As far as I know, I can't speak for other groups in the arthropods and reptiles and invertebrates, etc. But certainly in mammals, that looks to be the case. It is the major excitatory. It is a major excitatory neurotransmitter in the central nervous system. And it is the most common overall, and the references that I have say about 30 to 40% of all synapses, so we'll say all synapses in the central nervous system are going to have this, are going to have glutamate as a neurotransmitter. So it's major excitatory, and interestingly enough, the metabolism of glutamate, okay, glutamate metabolism, glutamate is also known as glutamic acid. The metabolism of glutamate can, and we'll talk about how that happens, but if I can metabolize glutamate in a certain way, I can actually come to another molecule known as gamma. I'll just write that down for you guys here. Gamma-Aminobutyric. B-U-T-Y-R-I-C, I believe, butyric acid. We commonly call this GABA, G-A-B-A. That's a little easier than saying gamma-aminobutyric acid. And I can metabolize glutamate into GABA. GABA, interestingly enough, is the most common, not the most common, is the second most common neurotransmitter found in the central nervous system. So it's second only to glutamate, and that makes sense because glutamate is metabolized to GABA, and GABA is the major, and you could probably guess this, inhibitory neurotransmitter in the central nervous system. All right, so we have glutamate, we have GABA. So when we talk about glutamate and GABA, Obviously, these are probably going to be important when it comes to medications or drugs like barbiturates and benzodiazepines that alter this, that depress the central nervous system. And you're absolutely correct. Most central nervous system agents that we run into do one of two things, work in one of two general ways. The first way is they inhibit. They work to inhibit the function, we'll say function or use of glutamate. Somehow they inhibit the glutamate function, the use, the transmission, etc. Or they can enhance the action of GABA. All right, and that makes sense because we just talked about glutamate and GABA up there, so that should come as no surprise. Since we're talking about central nervous system depressants, GABA right here is going to be critically important. And in fact, we are going to talk about GABA in a little more detail, and then in subsequent videos, I'm actually going to show you some molecular models. But it's actually easier at this point to kind of write stuff up on the whiteboard here just to build up the foundation. Okay, so when we talk about GABA, GABA actually has its own receptors. All right, and these are known as the GABA receptors. All right, and these receptors tend to be postsynaptic. And when we learn about neurons, we tend to want to think real simply. Like here I have the axon. Here I have an axon of one neuron. I have a synapse, and maybe I have the dendrite of another neuron. I have a synapse in there, and we like to think that I have a specific neurotransmitter in a neuron and a specific receptor for that neurotransmitter, and that neurotransmitter is released and it acts upon that receptor. The reality is that there are dozens, literally dozens and dozens. Okay, there are dozens of neurotransmitter types in the presynaptic neuron that can potentially be released, and then likewise, there are dozens of different types of receptor types. All right, there are dozens of receptor types postsynaptically, and it is this really complex interplay of dozens of neurotransmitters being released, acting upon dozens of different types of receptors. And it is this complex game, if you want to look at it that way, of all these neurotransmitters being released and all of these inhibitory or excitatory responses. And at the end of the day, when you look at everything that's happening at a certain point in time, is that enough to cause postsynaptic depolarization? All right, is that all? Because you basically when you look at if depolarization is going to happen, you remember studying basic neurology. It's the sum of all the inhibitory. Okay, it's the sum of all the inhibitory and excitatory. Okay, inhibitory and excitatory actions. It's a sum of all that, and if the sum is enough, okay, to push the membrane potential above the threshold, all right, you have depolarization of that neuron, okay? So when we look at giving drugs that act upon GABA, what's happening is we are going to shift the scales in the favor of not depolarizing that neuron. We are going to shift this right here, this summation, and we are going to hopefully, or maybe not hopefully if it's unintentional, or maybe it is intentional, but you still don't want that to happen. You want more inhibitory than excitatory, and you shift the scales away from depolarization. You prevent depolarization. Okay, so it's a very complex interplay of stuff going on here, but we tend to kind of simplify it. Okay, so when we look at the GABA receptors, we actually have several types. Okay, I have GABA A receptors, GABA B receptors, and GABA C receptors, and obviously there are lots of different polymorphisms. When we look at the primary GABA receptors that I'll be talking about are the A and B receptors, and the GABA A and GABA B receptors fall into the class of receptors known as ligand-gated ion channels. And I actually have done a whole video talking about ligand-gated ion channels, and actually talking a little bit about the GABA receptor in my physiology playlist if you want to take a look at that in more detail. These are ligand-gated ion channels, and the ligand that just happens to cause these ion channels to open, of course, that ligand is going to be GABA. GABA will act as the ligand that can attach to the active site of the GABA A and GABA C receptors. So the GABA A and GABA C receptors, when acted upon by the ligand GABA, will open. They have a little pore that opens up, and chloride ions will enter the neuron. And when chloride ions enter the neuron, that causes hyperpolarization of the neuron, of the cell membrane along the neuron. And what does that do? Well, if I hyperpolarize, if you kind of, and I'm really probably going to botch this up, but if you kind of look at how an action potential happens, generally the charge difference, it's much more positively charged outside of the cell than inside of the cell. So we say that the inside of the cell is much more negatively charged. So maybe here's 0 millivolts down here, and so up here is more positive. The potential is more positive. Down here, the potential is more negative. And what happens is, my neuron, maybe the resting potential is down here in the negative, and then I get these little excitatory and inhibitory responses, and so you kind of have this kind of thing going on. And what happens is, if I let's say I open some sodium channels, a bunch of sodium channels, and I shift this toward a positive. Eventually, what will happen is, when it gets positive enough, I'll have several channels, voltage gated channels will open up, and I'll have my depolarization, and then repolarization, things reset. And that point, at that voltage, okay, that happens, is called the threshold. All right, and there's generally kind of this distance here that I have to get to that threshold before depolarization occurs. Well, what happens when the GABA opens these ion channels and chloride flows in? Well, what happens is, instead of the resting potential becoming positive and moving toward depolarization, moving toward the threshold, what happens is, as chloride enters, the potential becomes more negative. It shifts down. So maybe if I have a whole bunch of GABA receptors opening, a whole bunch of chloride entering the cell, and normally my resting potential is right here, but I've shifted it down here. Well, what does that mean? Well, that means, in order for this neuron to depolarize, okay, I am going to have to work much harder. Look at that distance to get to the threshold. I'm going to have to work much harder to get to the threshold to cause that neuron to depolarize. And that is how this process of hyperpolarization works. by the GABA receptor. Now, that's the GABA A and the GABA C receptor. The GABA B receptor, interestingly enough, is kind of a quote-unquote turd in a punch bowl, if you will. He and or she, it, is the odd man out, and this is a metabotropic receptor, or a G protein coupled receptor. Okay, it activates a G protein. G protein has the 3 different subunits that travel out and act upon adenyl cyclase, and you have that whole mechanism occurring. And I believe at some point along the cell, these ultimately affect potassium channels. All right, so most of the effects, at least in mammalian physiology, most of the relevant effects that we're concerned about clinically will revolve around the GABA A receptor. And so when I talk about GABA, I am, from here on out, you can assume that I am talking specifically about the GABA A receptor. All right. So there we go. We've got kind of hopefully a better understanding of this. Let's talk about the receptor itself. The GABA receptor itself. Okay, so here I have the postsynaptic cell membrane. I've got the receptor here, like so. All right, the receptor has several little subunits that make it up. I'm just going to draw them there, and then there's a little pore in the middle. And if I were to kind of look at a cross section head on, it might look something kind of like a 5-leaf clover, if you will, where I have these little leaves here. So there's one. Hopefully I don't botch this up too bad, but 2. Let's see here, 3. I'm going to have a couple come in here, 4. Well, that's not looking terrible, I guess. 5, okay? And here I have my little pore in the middle, and when that opens up, that allows chloride ions to flow through that pore and into the postsynaptic neuron, into the dendrite there. Now, the receptors are composed of different subunits. You have 3 different types. You have your alpha subunits, your beta subunits, and you have your gamma subunits as well. And you have different subtypes as well. You have I believe you have up to 4 different subtypes of beta units. I believe you have up to 3 different subtypes of gamma and 6 different subtypes, I believe, of alpha units. In the human being, we care about the alpha 1 subtype. All right, so the alpha 1 subtype, all right, like this, the beta 2 subtype, and the gamma 2 subtype. Okay, so this is what the subtypes would look like in the mammal, in mammalian physiology. All right, so why do we care about actually looking at the subtypes? Well, the different subunits and the different subtypes of subunits have different actions, and different medications can act on these subtypes. So the alpha, we'll just start at alpha since that's the beginning anyway. The alpha subunit contains what we can call the benzodiazepine receptor. The benzodiazepine receptor site. All right. So benzodiazepines are going to work at the alpha subunit. Okay, whereas the beta subunit is going to contain the barbiturate receptor site. The barbiturate receptor site. All right. And then the gamma subunit is going to be affected by the benzodiazepines, but it is not a direct. It's not a direct effect. It's what's known as an allosteric. I believe that's how it's misspelled. Hopefully, if it's misspelled, hopefully you guys don't tear me up too bad. Which means that it is not actually the active site, but rather when benzodiazepines bind to the gamma site, they can enhance the activity of the intrinsic neurotransmitter GABA that's in the body. So it enhances how the receptor acts to GABA, but it doesn't directly affect the opening of the receptor like some of the other sites, particularly the beta site, as we'll talk about with barbiturates and what they can do. I think I have been going on for probably a bit too long. I'm going to cut this video off, and I'm going to make another video talking about how GABA and glutamate are synthesized, how they're stored, how they are released, and how reuptake and activation and elimination of GABA and glutamate occur as well. I believe that's worthy of its own video. Okay, guys, hopefully you're finding this helpful and informative. As always, thanks for hanging in there.